All right, in today's session what we are going to do? We are going to do the new chapter, that is electromagnetic induction. And in today's session we will have basic understanding of magnetic flux, Faraday's law, Lenz law, and that's it. In today's session this is what we are going to do. All right, so let us begin. First thing that we can do here is to understand that it is in this chapter actually electromagnetic induction. Electromagnetic induction. Chapter review: introduction, magnetic flux, Faraday's law, Lenz law, motional EMF, eddy current, self-induction, mutual induction, AC generator, right? Okay, is this possible that magnetic field can produce electric effect? As you can see, this chapter is all about that only. This chapter is all about that. Michael Faraday came up with this idea that if electric current can have magnetic effect, why not magnetic effect can be used to produce some electric effect? And with this simple idea he began his journey, and with all whole lot of experiments he came up with this thing, and the phenomena is called electromagnetic induction. As you all know, when we say induction, this means that it brings certain change in the behavior, in certain aspect in the body due to some external agent. What is happening? This electric effect is not brought from somewhere and given to, directly transferred to that. Actually what is happening? That ability, that capability is still there, that property is still there in that body made up of metal or something. Induction, electromagnetic induction. What is happening? Just break these three terms. When you are saying induction, induction means what? Is induction, you are saying induction of what? Electric effect. Induction of electric effect. Is it possible to induce electric current, electric effect in non-metal substance? Here we are not saying that. If you have a coil made up of glass, coil made up of plastic, or coil made up of some other substance, non-metallic substance, can this electric effect be induced in it? Answer is no. Answer is no. What we are actually saying, this electric effect is induced in metals, metallic conductor, coil or rod, or there are several other piece of conductor where this electric effect can be induced when magnetic effect is changed. Electric effect can be induced in metallic substance. When it can be induced? This was the question Michael Faraday asked. Michael Faraday, and he found with his multiple experiments that whenever there is relative motion between magnet and the coil, electric current is produced in the coil. But here it is quite important to note that electric current is not fundamental. What is fundamental? Induced EMF. EMF is induced, and that induced EMF is the fundamental quantity here. Okay, I give you this reason for this, some reason. What is the reason? The reason is you have a coil like this. It is not fully, connected. It is not complete. In this, if you follow certain condition, EMF is induced. EMF is induced, but not the current. EMF induced, but current is zero. No current is induced. No current will be flowing. No current will be flowing. Why? Ask yourself. Why no current will be flowing? All because this is not a complete circle, complete circuit. You need to complete the circuit in order to allow the current flow through it. Understood? So if you have complete circle, so EMF is there, current is there, both. Complete circle, complete circuit, then EMF is induced. When we understood electromagnetic induction, first of all, we have to understand what is magnetic flux. This is fine that when you are saying that with the help of his multiple experiments, Faraday found that whenever there is relative motion between magnet and the coil, electric current is produced in the coil. Fine, this is good. But first of all, what is it? What is it? How this is possible? Right? He found with this experiment, fine. But what is the reason behind it? What is the reason behind it? The reason is magnetic flux is changed. Whenever there is a change in magnetic flux, electromagnetic induction occurs. Now the next question comes, what is magnetic flux? So let us understand what is magnetic flux. First of all, we have to understand the magnetic flux. Qualitative idea and the quantitative idea. First of all, what is magnetic flux, qualitative, and you are saying that it is, and one more thing, important thing, magnetic flux through what? Through the coil, or magnetic flux linked with the coil, right? Magnetic flux through a coil is equal to the number of magnetic field lines. Magnetic field lines, right, passing through the given area of the coil. How do we measure it? Here it is how we measure it. We need to take the two vectors, magnetic field and area vector. Dot product of magnetic field and area vector. So magnetic flux is given as the dot product of magnetic field and area vector, right? So understand, this is the thing. You have the coil, this is the plane, area vector is always perpendicular to the plane of the coil, outward normal, that is important, and this is magnetic field. You got the point? Alright. Direction of area is along the outward normal to the surface. This you are aware. Theta is angle between B and A. B is magnetic field. Alright. Now let us move further. When the flux is maximum, the flux is maximum when theta is 0. That means if the plane of the coil is and magnetic field are perpendicular to each other. In that condition, what you will say that area vector and magnetic field vector are along the same line. In that situation, magnetic flux will be maximum. You are aware of that. Okay, now very important aspect. When this will, do you know that positive flux, negative flux, what is it? Okay, just have a look. Positive flux, magnetic flux is positive for, theta less than 90 degree. Okay, zero flux, theta equal to 90 or 270 degree. All right. Negative flux, when flux is negative for 90, between this, between 270 and 90 degree. Right? Okay. Now what is the SI unit of magnetic flux? SI unit of magnetic flux is Weber. 1 Weber equals 1 Tesla. It's wrong. Actually, wait. It is wrongly written. 1 Weber equals 1 Tesla meter square. 1 Tesla meter square. This is wrong. 1 Weber equals 1 Tesla meter square. 1 Tesla meter square. You must have heard this, and you will come across this thing. You will come across this thing very frequently, that 1 Tesla, 1 Tesla equals 1 Weber, 1 Weber Tesla equals Weber per meter square. Tesla equals Weber per meter square. Right? You will come across this thing, this unit. You need to be very careful about it. Okay? So magnetic field can also be considered as magnetic flux density. Did you get the point? Let me put it here. Magnetic flux density. This term you will require. In questions sometimes they will give you this. Magnetic flux density means B. It is actually B. Magnetic flux density. What is the unit of magnetic flux density? It is equal to Weber per meter square. Weber per meter square. Is that clear? All right. So let us move further. Now comes to Faraday's experiment. What is it? Michael Faraday. 2 experiments you can see here. One is this, another is this. What he did, he brought bar magnet close to the coil, and while bringing it, there is a change in magnetic flux, and the change in due to change in magnetic flux, EMF is induced in the coil, and since the circuit is complete, galvanometer shows the deflection. Okay, here also this is the experiment of mutual induction. Mutual induction. In one coil, you see here, in this coil, current is flowing. When you switch on this, current is flowing in this, and when variable current will be flowing, magnetic field lines will be passing through this, and when the magnetic flux linked with this coil changes, this is changing because magnetic field is changing, and when magnetic flux is changing, EMF is induced in it, and in this coil, although there is no source of current here, in this coil current is induced because of the change in magnetic flux, and hence this galvanometer shows a deflection. This is the concept of mutual induction, right? We will talk about that in detail when we'll move further. Right now, with his experiments, these 2 experiments, basically, you come to know that whenever there is change in magnetic flux, EMF is induced, electromagnetic induction occurs, and the second law says that what is the magnitude of induced EMF. Okay, so first law and second law. There is the first law, right? This is the first law. Whenever there is change in magnetic flux linked with the circuit, An EMF and hence a current is induced in the circuit. I have told you this very simple thing, that EMF is induced, that is fundamental, but current will also be flowing through that coil, will depend upon whether the circuit is complete or not. So take note of this. Okay. Now the second law says, what is the magnitude? Magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linked with the coil. Right? This is Michael Faraday's law. This is the basic, very fundamental. Magnitude of induced EMF is given using Faraday's law. Magnitude of induced EMF. So phi, magnetic flux, you have understood. Magnetic flux, rate of change in magnetic flux. Time rate of change in magnetic flux gives you the magnitude of induced EMF. Why this negative sign is coming in, he was not able to explain. He was not able to explain. In generator, what do you know? There is some mechanical energy getting converted into electrical energy. Earlier there was no electric energy. What was happening? Due to electromagnetic induction, mechanical energy, that means work is done on that. That work done in bringing this rod here is used, and due to that this mechanical work is converted into electrical energy. Let us take one question first of all. Let us take this. There are four options actually. Let us find out what is the value. This is B. This is B, 2 into 10 raised to power minus 2 Tesla. X at right angles to the plane of coil. That means theta is 0 degree. Area is given as 100 into 10 raised to power minus 2 square. N is 50 turns. The average EMF induced in the coil is 0.1 volt. That means EMF equals 0.1 volt. When it is removed from the field in t second, the value of t is. So what basically you have to do, EMF equals B2 minus B1 by t. Okay? B2 minus B1 by t. If you are saying that B2 minus B1, when it is removed from the field, that means B becomes 0, final B becomes 0, initial B is this. If you will say that induced EMF equals minus of this, okay? This is change in magnetic flux. Change in magnetic flux. So change in magnetic flux occurs due to the change in the magnitude of the field. So this is what you are doing. Flux we have understood. Theta is 0 degree. So flux will be what? Flux will be B into A, right? B into A. But what you are required to do? EMF equals minus phi 2 minus phi 1 by t. This is what you are doing. So B2 minus B1. So what you will get? It will be, just put the values, all the values actually. What you will do? 0 minus this value, 2 into 10 raised to power minus 2. Alright. Time we have no idea about. Area is 100, that means 100 into this. So 10 raised to power minus 2 is coming in. Alright. 10 raised to power minus 2. Okay. 10 raised to power minus 2. Alright. And EMF is known to us. EMF value is 0.01 volt. 0.01 volt. That means 10 raised to power minus 1. 10 raised to power minus 1. This is the value. Okay. Now can you do it? This will go up here. I want you to find this out, as this will be minus. So 2 divided by, what is happening? Oh, wait. There is one more thing. 50 turns. Actually 50 is also multiplied with this. So 2 into 50 into 10 raised to power minus 4 divided by 10 raised to power minus 1. So what is the answer? What is the answer? This will be 100 minus 2, 10 raised to power minus 1, right? 10 raised to power minus 1 second. That means 0.1 second. 0.1 second is the value of t. Lenz's law gives us the direction of current. And when North Pole is brought, mind it, when North Pole is brought closer to the ring, metallic ring, yes, of course, metallic ring, what is happening? Flux is changing. Okay? Flux is changing. And why flux is changing? Because the magnitude of magnetic field is changing. As you see here, the separation is changing. Right? You see, you are bringing the North Pole to the, along the axis of the coil, closer to the coil, right? Okay, see what is happening. Lenz's law is saying, and Lenz's law is the consequence of conservation of energy. Conservation of energy. This can also be asked, right? Lenz's law is the consequence of conservation of energy. What he is saying, the work done in bringing it closer to the coil. See what is happening. Earlier, when the two magnet and coil, when both the objects were at rest, no work was there, no energy was there. Now what is happening? Energy is given to this. By doing some kind of work, energy is given to this. Now this energy and the energy induced in it must be add up to zero, must be added up to give the zero value, because earlier there was no energy. When they were placed at certain distance apart, they are kept stationary, then there was no energy in it. When mechanical work is done, that mechanical work will induce the same amount of energy, and when you add the two energies, it must be equal to zero. So with the help of this law is saying that the induced current has a polarity which tends to oppose the cause of change in flux. Oppose the cause of change in flux. Lenz's law gives the direction of induced current. It is the consequence of conservation of energy. Now see what is happening. North Pole is brought here. When North Pole is brought here, brought closer, the ring has a tendency to oppose the North Pole. To oppose the North Pole, what type of current? Anti-clockwise current will produce north polarity of magnetic field. So in this coil, anti-clockwise current will be induced. That will oppose the North Pole. Now when this bar magnet is taken away, what is happening? Bringing closer is the cause. In the beginning, bringing the bar magnet closer was the cause. Induced current in the coil will try to oppose it. That means it will push the bar magnet away. Now if you are taking the bar magnet away from it, the coil will have current that will try to bring the bar magnet closer. Whatever you are doing, the current in the coil will try to do the opposite. Right? Whatever you are doing, you are bringing closer, it will try to push it away. If you are taking away the bar magnet, the current in the coil will tend to attract it. That means when the north pole of the bar magnet is taken away, current induced in it will try to produce the south polarity so that the north pole can be attracted. It will try to bring the bar magnet closer because you are taking it away. So in this now, when the north pole of bar magnet is taken away, coil will have south polarity. For that, clockwise current. Did you get the point? Clockwise current when the north polarity of bar magnet is taken away. Anti-clockwise current when north polarity of the bar magnet is brought closer. Right? So current has a tendency, current tends to oppose the cause of change in magnetic flux. Change in magnetic flux. We will have more examples based on this Lenz's law because this is required. This is the coil. This is the coil. Observer 1, observer 2. Observer 1, observer 2. What is happening? A bar magnet, north polarity of bar magnet is brought closer to this. I want your answer within this. To observer 2, the current induced in the coil will be clockwise or anti-clockwise. The question is basically, for the two observers, will the direction of current in the coil, will the direction of induced current in the coil be same or different? This is the question. Observer 2 will notice the current to be ACW. To observer 1, it will be clockwise. Whatever this is there, opposite to this. It has to be opposite. To this observer, it is anti-clockwise. To this observer, this anti-clockwise appears to be clockwise. Okay? So, one question can be asked from this. Got it? It has to be opposite. Seen from the other side. This type of question will be there. Okay? Let us move further. You have a coil here, you have a coil here. In this wire of infinite length, current increasing. So loop 1 and loop 2. See what is happening. This long straight conductor has increasing magnetic field And what is the direction? Direction of existing magnetic field, here in this will be outward, here it will be inward. So, if the magnetic flux is changing because of the increase in magnetic field, then what? The current in this will try to reduce the field. To reduce the field, the direction of field due to induced current should be outward. And here in this, it has to be inward. So it will be anti-clockwise ACW. Here it will be clockwise. Now, if the wire has current I decreasing, one loop here, another loop here. Existing magnetic field is inward, it is outward, it is decreasing. It will try the induced current in the two coils, 1 and 2. In both the coils, induced current will try to increase the magnetic flux. So then it will be direction of induced current has to be clockwise, anti-clockwise in this direction, anti-clockwise in this first loop, and then clockwise in this loop. Tell me, is this clear? If the cause of change in magnetic flux is decreasing magnetic flux, then what will happen? Induced current in this will try to increase it. In order to increase the magnetic field, it will come in the same polarity, right? This will add to this existing. Here in this one has to be opposite to this, right? Because it will try to decrease. The induced current in it will try to increase the existing field in this question, right? It will try to increase. Here in this, it will try to decrease, and it has to be opposite, right? Now let us move further. Suppose you have this magnetic field into the page magnetic field, into the page magnetic field, and in this a loop taken away, a loop is taken away from it. The change in magnetic flux will be there. So it is increasing or decreasing. When the loop is taken away from this, when the loop is taken away from the magnetic field region, what will happen? Magnetic flux will decrease. Magnetic flux will decrease. The induced current in this will try to increase it. In order to increase the existing field, it has to go this way. Induced current will be clockwise. If you have another loop, it is taken inward. It is taken inside this. It is increasing. It is increasing. Flux is increasing. Induced current in the coil will try to decrease the existing field. That means here in this, outward, and it has to be anti-clockwise direction. Okay, this is the basic idea behind it. Now let us move further and try to understand what is the motional EMF. We need to find out the direction of induced current when a loop is moved in the magnetic field region. So that we are saying as motional EMF. Let us talk about this. EMF induced in a coil due to the motion. Okay, what is the concept? There are two types of motion you can imagine, and one type is, suppose this is a metallic ring. This is a metallic ring, and you have a rod. You have the rod, and this rod is, one end of the rod is placed on the ring, on the circumference of the ring. Another end is acting as the center, right? And length is radius of loop, right? Okay, and now what is happening? This is rotating. Rod is revolving. Okay, this is one scenario. Another scenario is, there is a rod framework in this manner, the wire, and the rod is placed in this. Okay, so this completes the loop, right? This one is also metal. This framework is also of metal, and this is also a metallic rod. Okay, now the magnetic field, here also it is into the page, magnetic field. So here in this, rod is rotating. Rod is rotating about one end. Rotating about its one end. Its one end. Here, rod is being translated with this velocity. Right? Earlier, you may assume that it was here, it is taken to this. So, what is the cause of change in magnetic flux? Look at this. Magnetic field B is fixed. This one is not changing. B is constant. Magnetic field is constant. Okay, here also it is constant. What is changing? When the rod is taken away, it is moved with this velocity v, what is happening? This area will increase. Area of the loop will increase. Here also area is changing. Area, when it was here, it is changing. Right? So area is changing. Rod is rotating here, and here rod is moved with velocity v. Velocity v. Here omega equals 2 pi into n. N is what? RPS. Rotation per second. Rotation per second. Okay. What will happen? Magnetic flux will change in this. Magnetic flux will change in this also. What is the relation? Here, induced EMF will be magnitude d phi by dt equals BLX. Why so? Flux equals what? B into A. B into A. Mind it. B into L into X. Area is this, and cos 180 degree. So minus if you are taking this minus d by dt of this, it will be minus of this, right? So it will be ultimately BL, these two things are constant, and this will be dx by dt, and finally you have this BLV. BLV is the magnitude of induced EMF. If current you are required to find out, it is BLV by R, where R is what? Where R is resistance. Resistance of the rod. Okay? Resistance of rod. This is the induced current, and this is the amount of induced EMF. Now in this, what will happen? Let us quickly have the picture. EMF equals half BL square into d theta by dt. What is theta here? This is theta. Okay, if you will look at it, L is the radius of the loop, that means length of the rod. Okay, so what you will get? EMF equals half BL square omega. What is omega? Omega equals d theta by dt, and this is angular velocity of rod. Angular velocity of rod. So finally you are going to get this, and this has to be measured in this term. Omega equals 2 pi into n. Be very careful about it. 2 pi into n. Omega is, for one rotation, it is 2 pi. Theta is 2 pi. For n rotations, this is number of rotations per second. So you got this angular speed, angular velocity. So in both the cases, you will have induced EMF. They may ask you, what is the potential difference across the ends of the rod? Potential difference of the ends of the rod when this is the scenario. Okay? So this was the basic idea behind motional EMF.